So in the last video, we talked about the idea of phase analysis, what it is. In this video, we're going to talk about how we can use it for modeling, okay? So we just talked about the logistic growth model. And so the logistic growth model we started using because it was more realistic than exponential, right? If you've got something that's growing exponentially, it can't keep growing forever. It's got to settle in and flatten out at some point, right? But there are things about the logistic growth model that really aren't realistic for populations either, okay? And so a big thing, probably the most important, if you think about a population model, so for example, we talked about populations of birds or things, what's going to happen to the population of any sexual dimorphic species, any species that has two different sexes to reproduce, if you've only got one individual, right? So for example, I think there's one white rhino left. Is that species going to survive? No, right? Because there's not two to reproduce. And in fact, you need some sort of minimum viable population, right? Even two isn't enough, because then if they had children, all their children would be related, and you would have not enough genetic diversity to survive, okay? And so the logistic model has been updated by people who really study animal populations to something called the alley effect model. So this is, I don't actually know where this name comes from. I'm assuming it's somebody's name. But the alley effect model says basically you want to have so let me kind of just outline what the behavior looks like, and then we'll talk about the model, right? So when 0 is less than x is less than some threshold, which we'll call A, the population decreases. Okay, so if you're less than A, you don't have enough animals to genetically reproduce. There's not enough to survive. They can't, whatever, right? So that's not enough to survive. If you're in kind of the sweet spot, A less than X less than B, your population increases exponentially. Okay? Just like it did with logistic growth, if you've got more than A, then you can reproduce, and they grow until they get to the carrying capacity B, right? So this is the same carrying capacity we saw in logistic growth. And when X is greater than B, because you're past that carrying capacity, your population declines. Okay? And so if you think about this model, you might say, okay, what's the differential equation? It might be really hard to think about what that differential equation would look like. But if you think about what the phase analysis should look like, so you've got 0, you've got A, you've got B, right? And so what you know is that at 0, the population isn't going to change, right? Because it's got to, if the population's 0, it's going to stay 0. At A, the population isn't going to change, because if you're below that, you're decreasing. If you're above that, you're increasing. Here, you're right on the edge. And at B, your population isn't going to change. These are your three equilibria. Between 0 and A, your population is decreasing. So dx dt needs to be negative. Between A and B, it's increasing, right? And it's going to look a lot like the logistic model. So it increases between A and B, and then when you're greater than B, it decreases again. Over here, when you're less than 0, of course, that's not really part of our model, but you can imagine, because you can tell kind of what this function is, we can clearly set up a polynomial that does this, right? So if you think about finding a polynomial that fits this, this is a polynomial which has 3 roots. It's got a root at x equals 0, at x equals a and at x equals b. So x times x minus a times x minus b, right? That would be a polynomial with the root at 0, a and b. We can put in some sort of growth term, right? So if you think about, if you just do x times x minus a times x minus b, that's one particular fixed polynomial. Add in a coefficient r, and you can stretch this up or down, okay? So if you make r larger, the peaks will go higher and lower. If you make r smaller, they'll be closer to 0, so that's kind of going to be your growth parameter. And then one other thing to build a differential equation from this, r times x minus a times x minus b actually doesn't look like this. So if you remember back in the day, thinking about polynomials, this is going to have, the first term is going to be rx cubed, right? So r is a positive number. Rx cubed is going to give you a graph that looks something like this, okay? So it's going to increase over here, whereas this one decreases, and then increases, and then decreases. So in order to get this to actually be the one that we want, we have to flip it over. So negative rx times x minus a times x minus b will flip this, right? And so then we have something that decreases, then increases, then decreases, okay? But this is the alley effect model. And dx dt is equal to negative rx times x minus a times x minus b. And you build the model in this way. So they said, okay, we're going to set this to be our minimum viable population, this to be our carrying capacity. So the model then has to look something like this, okay? So that's one example of how this works. Another example to kind of talk through is what happens to our logistic model if we add in hunting or something like that, okay? So if you think about, go ahead and erase all of this, modifying a model we already have. So, so taking the logistic model and modifying it. So let's actually put put up our logistic model. Dx dt equals negative r over k x squared plus x plus rx. Yeah, that's what I thought. Okay. Always have to look at my notes to be sure. So dx dt equals negative r over kx squared plus rx. So remember that looks like this. We've got this parabola that goes up, okay? So that's the graph of dx dt as a function of x, okay? And so say we modify this model. So say we decide to hunt, what's the variable that I use here? Let's see, h. So we decide to hunt h animals each year. So you're removing h from the population each year. That's going to give you a minus h in your differential equation. Okay? So minus h, because now the growth rate is going to decrease by that h amount each time because you're hunting them. So if you think about what that's going to do to the graph, if you subtract a constant from a parabola, what that does, think way back to the beginning of Calc 1, pre-calculus, back when you did algebra, subtracting a constant is just going to move the whole thing down by h units, okay? So it's just going to shift everything down by h, and so the peak of your graph is going to be there. And you can see what that's going to do is it's going to move your parabola down. It's also going to change your equilibrium points, Okay? So when you move this down, suddenly now, not only has your peak gone down to somewhere here, but your equilibrium points have moved in. You can see that you now no longer have a viable minimum. Okay? We'll actually look at a specific example of this in a second. Right? So the minimum population has gone up from 0. And that's because if you think about it, say you're hunting 10 animals every year. If your population is less than 10, you're going to hunt all 10 of those and your population is going to go negative, right? Similarly, your carrying capacity is dropped because if your carrying capacity is, say, 200, every year you're going to hunt 10 of those 200 animals, and so your equilibrium will become 100 and somewhere between 190 and 200, right? Because if you have 200, you'll hunt 10, it'll drop down to 190, and then it'll start to increase again, but then you'll hunt more, and so the equilibrium is somewhere in between. Okay? So if we look at a specific, kind of some specific details here, so I'm going to erase the H and go back to this, just to kind of look at some features of this graph. So you've got your parabola. The nice thing about this parabola, it's symmetric between 0 and k. And so your peak in the center, the place where the growth rate is largest, is at k over 2. And if you plug that into your equation to find out what you get when x is equal to k over 2, this is going to become r k squared over 4 divided by k plus r k squared over 4, and you can manipulate that around, and what you find is that this peak occurs at rk over 4, right? And that just comes from plugging in k over 2. So negative r over k times k over 2 squared plus r times k over 2 gives you negative rk over 4 plus rk over 2. And so when you combine these two fractions, that gives you rk over 4. Okay? So without the hunting, your maximum occurs at k over 2. It's equal to, your derivative maxes out at rk over 4. That's the maximum that the derivative hits. You can analyze what happens when you subtract h and figure out what this new curve looks like. So if you look at negative rk x squared plus rx minus h, well, the nice thing is you can figure out what the zeros are. So what are your new equilibrium points? Give myself some space here. So this is going to be dx dt equals 0 at our new equilibria. You can find the places where this is equal to 0 using the quadratic formula. So negative r plus or minus the square root of r squared minus 4 times negative r over k times negative h all over negative 2r over k, right? That's going to give you a formula for this point and this point. And if you've got specific numbers, you can figure out what those are. Find your equilibrium. You can find your maximum derivative by plugging in k over 2. And you can think about other things, like, for example, what's the largest number of animals that you could hunt and still have this population not die off? Okay? So how much can you move this curve down without the population always decreasing? So that's another example of a kind of question that you can model. If you think about that question, how much can you move this graph down before the population is always decreasing? You'll see pretty quickly the answer is rk over 4, right? So if you took h equal to rk over 4, Well, if you take h equal to rk over 4, that's going to move the graph down by rk over 4, which means that your new graph, let's erase this old new graph, if you move it down by rk over 4, your graph is going to look something like this. Okay? And so you might look at this and say, okay, well, no, that's always negative, right? That's always going to be decreasing. But it's not quite. Okay? So if h is equal to rk over 4, you have an equilibrium point. Where dx dt equals 0 at x equals k over 2. So what this actually looks like, in this case, the phase analysis, if you think about it, if x is equal to k over 2, the population stabilizes. If x is greater than k over 2, it decreases until it gets to k over 2. If x is less than k over 2, it decreases until it hits 0. Okay? So rk over 4 is called, rk over 4 is called the maximum sustainable yield. So if you're thinking about your population as something that we're hunting, or this is used a lot with fish to decide what you can remove without killing off the population entirely. So if this were a population of fish, you could remove rk over 4 every year without the population collapsing. Okay? Now, again, would you want to go exactly to that rk over 4? Probably not. This is a little dodgy, because if this model is even off by a little bit, you get into this zone where the population decreases catastrophically. Okay? So you can get yourself into trouble kind of skirting these values. But that's the idea. Okay? So, how am I doing on time? I'm going to pause this one here, and the next one we'll look at a different way to change this model.